So today I wanted to show that a group of order less than or equal to 5 has to be abelian. First of all, a group is a set with an operation such that it follows these 4 properties: closure, associativity, identity, inverse. And a group is called abelian if for every pair of elements they commute AB equals BA. This is not given in the definition of a group, so not every group is abelian actually, but a lot of smaller groups are abelian, and in fact any group of order less than or equal to 5 is abelian. So that's what we're going to show today. So we're going to start with 1, a group of order 1. So it just has one element. I'm just going to call it X. From the definition of a group, we have identity. So we have to have an element called identity. And that element, when you multiply with any element, you get the same element. So X times X equals X times X. So this is abelian. I'm just gonna erase this. This is pretty simple. So for a group of order 2, we have 2 elements. And then again, from the definition, we know that one of the elements has to be the identity element. So I'm just gonna call one of the elements E and then the other element A. So A is not the identity element. For this, we can actually just use this definition right here to show that this is abelian. So the first pair is E times E, has to be E, and then equals E times E. And this is because E is the identity. So when you multiply the identity by E, you get E. The same thing goes with E times A. E times A, then you get A, and then A times E. Or, and then the last possible pair, because here we show that E times A equals A times E, the last possible pair is A times A. And what's A times A? Now we are going to look at this inverse. So A is an element in a group, so it has to have an inverse. So there has to be an element in G such that A times something is E. And then this is clearly not E, because A times E is A, and then we know that A is not E. So this element has to be A. And the reason for that is because we know that G is a group, so every element has to have inverse. So we know that A times A is E. So A times A is E, so A times A is, again, I know that these 2 lines look a little dumb, as in like you have E times E equals E times E. But if you see this definition, you have to you pick a pair of elements. Not this one, sorry. This one. If you have 2 elements, they could be the same, then you can reverse the order. I'm doing, for this first example, I'm following this definition strictly, but for the rest of the video, I'm not going to do the same element, different order, because it's pretty obvious. So now, for a group of order 2, we checked all the pairs of elements, and then they commute. The order of multiplication doesn't matter, so we know that G is abelian. Now we are going to move on to a group of order 3. Going to actually move this to the side in case we need it later. So group of order 3. So a group has 3 elements, and then because of this, this identity property, we know that one of the elements has to be the identity, so we're just going to call it E. And then it has 2 other elements And we're gonna just call them A and B. The naming doesn't really matter. We just have to have some sort of name so that we can start playing with them. And then first thing we can think about here is what's A times B? Because it has to be defined, right? And then because of this not associativity, because of this closure property, we know that A times B is in G. So it's one of these three elements. So there are three possibilities. A times B is A times B is or B. And then which one of these is the correct one? So this is actually not correct. The reason for that is we know that G has inverse. I mean, every element in G has inverse. So what happens is like A times B equals A. This would imply that A inverse A times B equals A times inverse A. And this would imply that B is A inverse. I'm sorry, B is the identity element, which is contradiction. Because when we named each element, we specifically said that G has three elements, and one of them is E, and one of the other ones is B. So B and E cannot be the same. The exact same argument can be applied to this. So A times B is not B. So A times B has to be E. So using this, we can start following the definition here. So there are there are a few possible pairs: EA, EB, AB. So E times A is A times E. This is pretty easy because E is the identity element. So this has to be true. E times B equals B times E. Again, this is pretty obvious too, because E is the identity element, and then from the definition, we know that E times B has to be B times E. And A times B, we proved that it was supposed to be E from here. Then what about B times A? We want it to be E, right? Because we want to say that A times B equals B times A. And we can actually use the exact same argument. So is B times A E, or B times A equals A? B times A equals B. One of these has to be true. And then we can use the exact same argument as this one to show that B times A is not A and B times A is not B. So we know that B times A has to be E. So we can show that A times B equals B times A, which is the definition of an abelian group. So here we show that a group of order 3 has to be abelian. And then I'm gonna move this again to make some room for a group of order 4. And a group of order 4 is a little bit more complicated. I am going to call this EABC. So this is so far the same thing. A group has to have the identity element. So I'm just going to call one of the elements E, and then the other 3 ABC. And then, so far what you might have noticed is if you have a group of order 1 or 2 or 3, the group structure can be uniquely determined. As in, we do not have like different cases. For example, when we were talking about a group of order 3, we know that A times B is always E. There is no group in this world where A times B becomes B if the group has order 3. And that's not true in this case, as in there are 2 possible structures for a group of order 4. And then to simplify the argument, I'm going to use this theorem called Lagrange's theorem. So Lagrange's theorem states that every an order of every element, I'm gonna call it X. Order of the element divides the order of the group. So we are going to use this property to show that this group G has to be the identity, a nonabelian group. So from this, we can start thinking about what are the orders of each element A and B and C. So since the order of group is 4, because that's what we're doing here, we know that the order of each element, the possible values for the orders of elements are 1 or 2 or 4. And it is pretty clear that 1 is reserved for the identity element. So these 3 guys have to be one of 2 or 4. So we are going to split this into 2 cases. The first case is there exists an element in G such that the order is 4. And we can just, for now, A and B and C, those are just names. Like, we didn't really specify any properties, so without loss of generality, we can just assume that order of A is 4. If order of A is 4, what happens is we have A squared, A cubed, and A to the 4th. This is E. And if you think about it, this is actually the same set as E, A, B, C. So you can represent every element in G as a power of A. And this actually simplifies the proof a lot, because for all, or I guess we could also call this A to the 0. So if you represent this E, A, B, C as A to the 0, A to the 1st, A2, A3, we can represent it like this, right? Then what happens is that for all, if you take any 2 elements from this set, we have AI and AJ, where I and J are between 0 and 3. Then what we wanted to show was this AB equals BA for any pair of elements. But AI times AJ is AI plus J, which is AJ plus I, because, adding 2 integers, the order doesn't matter, so AJ times AI. So for any pair of elements in G, the order of multiplication doesn't matter in this particular case. So we're done here. The second case is a little bit more complicated. So going back, each non-identity element has order either 2 or 4. And then we assumed, in this case, that there was an element of order 4. And then in this second case, we're going to assume that there is no element of order 4. That means every non-identity element has order 2. So this gets tricky, but the reason for that is, so for each pair you have, so each non-identity element is the inverse of itself. But what we want to show is for, again, every pair, the order of multiplication doesn't matter. So what we need to figure out is, for example, A times B is B times A. What we need to show is something like this. And actually, again, in this case, we are assuming that every non-identity element has order 2. So far, we don't have anything specific about A and B and C. They are symmetric. So actually, if we can show that A times B equals B times A, the exact same argument can be applied to B times C equals C times A, and A times C equals C times A. So as long as we can show that A times B equals B times A, we'll be good to go. So what happens here is, so what's A times B? What is this equal to? So this is going to be a little bit similar to the previous argument for a group of order 3, I think. But this has to be one of E or A, B, and C. So let's look into this. So this is actually not possible because A is the inverse of itself. But if this was true, B would be A inverse. Then this would imply that B equals A, which is clearly a contradiction. The second one, A times B equals A. So this would imply that if you multiply A inverse from each side, you would get B equals E, which is also a contradiction. The same thing applies here, because you can just multiply B inverse from each side. So we know that A times B equals C. So basically what happens is if you take two non-identity elements and then multiply them, you get the third one. You can apply the exact same argument for B times A. So for each E, A, B, C, you can check if B times A would be equal to that. And then you will get to the conclusion that B times A equals C. So now we have A times B equals C, and the B times A equals C. So we have A times B equals B times A. And then the exact same argument can be applied to B times C and the A times C. So we show that this would be abelian. And then since for a group of order 4, these two are the only possible cases, we show that every group of order 4 is abelian. So the last one, group of order 5. So again, I'm just gonna call it E, A, B, C, D. And this is actually easier than the case of, 4, which sounds a little bit weird because 5 is a larger number, but it's actually simpler to prove that this group has to be abelian. We're gonna use a similar argument. So this Lagrange's theorem, I'm going to use so every element in a group has an order that divides the order of the group. So we are going to consider what the order of A is, or anything actually, any of these 4 elements. And then since the order of group is 5, that means the only divisors are 1 and 5. And then again, 1's only reserved for the identity element. So the order of A has to be 5. What it means is that G has 5 elements. But this actually can be written as A0, A1, A2, A3, A4. Then this is the exact same case as this one. Since every element can be written as AI and the AJ, AI times AJ equals A to the I plus J, which is A to the J plus I, which is a to the j times a to the I. The exact same argument can be applied here for all ai a to the j in G, ai aj equals aj ai, which effectively proves that every pair of elements in G, the order of multiplication doesn't matter. So we just shown that every group of order 1 or 2 or 3 or 4 has to be abelian. And 5 is actually the largest number for which this holds. Actually, for a group of order 6, it is possible that a group is not abelian, and that group is called a symmetric group of order 3. So this is a permutation of 3 elements. So what you could say from this is, to have a non-abelian group, you have to have a certain number of elements. So creating a non-abelian group is actually not that easy. So if you have a few number of elements, like 4 or 5, creating a complicated structure like non-abelian groups is not possible.